Hi, everyone. Hey, David.
Hey, Tiffany. Good to see you.
Hey, yeah, good to see you. So David, the convention for the class is that we're gonna wait for everyone for about like 5 minutes. And after that, I'm gonna start to talk about the logistics of the class, and then I will introduce you, and then you're gonna start.
Sounds good.
Also, David, I don't know if you know about that. Like in your container, you used to have what is called like fuzz dash example folder. It
Yeah,
seems that it's no longer over there. Okay, you know about that.
yeah, it's fine.
Great.
I
Okay,
cut it out. Yeah.
cool. All right, guys, let's start to roll. First of all, let me share my screen with you. Give me a sec. Oh, actually, you cannot see my screen right now. Hold on. All right, can everyone see my screen?
I can see
Yes?
the PowerPoint. Yes.
Yes, awesome. The PowerPoint, exactly. All right, guys, let's start. Hello, everyone. Welcome back to our class, CSE545 Software Security. And in this week, we are gonna, I invited Professor David Bromley to give us a guest lecture in terms of fuzzing, because he is the guru of fuzzing, and it's really my pleasure to have him here and to talk about all the fancy part about automatic fuzzing. So before that, let's talk about the course logistics first. First of all, thanks for the poll. And I see many of you would like to start CTF earlier. So let's start it earlier. Let's have it right after Thanksgiving. We're gonna start CTF from the Saturday right after Thanksgiving, which is November 28th. And it's gonna last from November 28th to December 1st. So it's about a week, 7 days. And we will have about 10 challenges over there. The exact time of when to start will be announced in our announcement channel in the Slack. So stay tuned for that. Also, our last assignment for Baby Heap is currently going. I would like to give you guys a hint, as I have mentioned in the announcement. You want to make sure that you want to overwrite the GOT table so that you can convert a heap vulnerability to a format string vulnerability. And the way that you make that happen is to overwrite the put function in the GOT entry and then replace that with printf. Also, you want to make sure where the printf is. You want to find the instruction that will lead you to the function of printf so that you can use printf instead of using put in your binary. So that's a hint. Hopefully that will help you with your challenges in Baby Heap, especially for level 5 and probably level 9 as well. So yeah, so take that. Also, if you still have any more questions, feel free to let me know or let the TAs know. We'll have TAs office hour right after this course, and take this as a good chance for you to get a hint or solve your confusions, for the challenges, for the questions, for whatever you have in terms of heat, in terms of the assignment. Okay, and then next is, let me just welcome Professor David Bromley, and he's gonna give us this lecture. And as I have said this many times again, but I would really like to repeat that. Like, David is a professor from Carnegie Mellon, and he's also a founder of For All Secure. I really like the fact that David is working on both academia and the cutting edge of industry for fuzzing. And his research is not only just for fuzzing, but due to the limit amount of time, we can only have David here to talk about fuzzing today, which is unfortunate, but he has a lot of very fancy papers and talks online. So you can also just like Google David Bromley and you can watch his videos, which is also fantastic. It's one of my favorite. Okay, now I'm gonna hand my screen and my speech to David and have David start.
Hey, it's great to be here, Tiffany. It's great to join the class. I hope you all got a chance to watch some of the videos that I posted. As I said in those videos, originally I wanted to give a deeper introduction to fuzzing, but I got kind of hit upside the head this year where I came down with head and neck cancer. So my voice sounds very weird. So I've already gone through surgery and radiation. I'm recovering, but it has kind of limited the amount of time that I could put into this. Tiffany, everyone should have gotten the README, right?
Yes.
Cool. So really my goal when I was thinking about what we could do in this class is instead of focusing on the latest research, I thought it would be very valuable for anyone who's taken a class in software security and computer security to actually have some experience fuzzing. And so I wanted to walk through a pretty simple example of how you'd go about this in practice. And I think just like you're doing in this class, often you can have a lecture where you understand the concept, but when you go to actually do it hands-on, questions come up. And so I wanted to take that approach. So the very first thing in this README, if I just bring it up here and let me figure out how to share my own screen. Everyone should be able to see my screen, right?
Yes, I can see it.
Cool. So there was this in fuzzing class exercise. I assume everyone has it. So the first thing I'd like to do is just spend a little bit of class time making sure everyone can get it running and do really this first example of how do you go about doing a simple exercise with AFL. And so after I give you a little bit of time to do that, I'll go through an example solution. So first, I'll just show you guys how to run the Docker container. It sounded like some people were not as familiar with Docker in this class as others. Docker is amazing. It's quickly becoming the industry standard for reproducible environments. So if this is the first time you use it, I'm sure it's not going to be your last. So to run it, simply do a Docker run. This is saying be interactive and attach your terminal. And this -v is saying mount my current directory in the mount directory inside the Docker image. And this is the Docker image itself. So after you do that, you should get a shell. If you've not done this command before, it may take a few minutes while it pulls the image from Docker Hub. And then just go to the mount directory underneath the AFL example. And what I'd like you to do, and I'll give you about maybe 10 minutes to do that, is take this simple test me program here, like we covered in lecture, which is simply BAD, if the buffer is BAD built-in trap. And you'll also see an undefined use here. And I had that there for if someone wanted to look at libfuzzer, it would raise an uninitialized use there. But just look at this example. The goal is to reach this built-in trap. That's an example for the bug. And so I wanted people to take this program, compile it with AFL, and be able to run the actual AFL fuzzer. So one hint I will give people is to go to the Google AFL page if you've never ran AFL before, and just quickly read through the README. It's a pretty good README on how to go about using AFL, and then how to actually fuzz a binary. So the actual fuzzing a program would be something like this. And so is this an appropriate way to do it, Tiffany? We give them about 10 minutes to see if they can get through this?
Yes, positive.
Cool. And so I will just stop there and set a timer for 5 minutes. And then I will join you and show you how to solve it.
I had a quick question. You mentioned the instructions on how we could perform the fuzzing was in Google AFL. Okay, sorry.
Okay, hopefully everyone got enough time to go through it. Man, in the class, you'd kind of ask people, raise your hand if you were successful. I don't know how you do that on Zoom, so hopefully some of you were successful out there. Maybe we can do it in the chat box. If you were successful, can you say so in the chat box? And then how do I see the chat box? There we go. Oh yeah, a number of people were successful. Nice, everyone. This really hopefully shouldn't be too hard. There's a couple things that you need to know that are just very much Unix idioms. The first thing is, I'm assuming everyone here knows about make files, but when we're making the program, typically you're going to be using an environment variable like CC. And so the first step is that you have to compile the binary with AFL GCC. And what that does is that instruments the binary, as I discussed in the video. That instrumentation keeps track of coverage. So as AFL is coming up with new tests and running the binary, it's collecting coverage information about that test case on that binary. And it's doing this as part of corpus management. And so if you simply do CC equals AFL GCC and make, you'll get, you'll instrument the binary, and it'll just produce, a normal test me binary with that AFL instrumentation. If I go here just to my in-class notes for AFL, for the solution, you do CC AFL GCC make. And then the second thing is you actually want to run AFL. So AFL has a corpus that it's creating. It's creating a set of test cases. And it differentiates between the input set, the set that you give it, and the set of outputs that are going to be created. And so you make two directories, one just for your input corpus and then one for AFL to use. And we're going to copy good.txt inside in. Now, if you were fuzzing, for example, an MP3 player, something processing images, as we're going to look at in a second, something processing XML, you may put many, many different files in here. It doesn't need to just be one. And these are what we're going to call the seed corpus or the seed set. So you may have heard this term seed. The second thing that you do is you run AFL, and AFL takes the input corpus and then output corpus for the out directory and the binary. Oops. And then finally, one of the things that you have to tell AFL is where to put the input file that it created. Remember, at a high level, what AFL Fuzz is doing is it's creating input files. And you have to say where to put that input file. So for example, if test me required a -i argument, you do -i at. And that at is just a special symbol that AFL came up with that you're not going to see normally used to signify where to put the file name that AFL created. And so if we do that and make sure you expand your monitor, you should see AFL start to run. And this is a pretty simple case, but what you should start seeing is the number of total paths slowly increase. This means AFL is slowly getting coverage of the program. It's generating a test suite that gives you coverage of the program. And then there's a variety of other things that it's talking about here, such as the total runtime, the time since the last new path was seen. These are good statistics just to see how long you've been fuzzing and when the last time AFL found something interesting, as well as what it's doing as far as stages. So AFL has a portfolio of different approaches it takes, and those are documented inside some of the technical details, and this will tell you what stage it's on. One of the things I want to call your attention to is this execution speed. So the execution speed is how quickly AFL is executing that, that particular program. And what you want to see is a higher execution speed means that you're trying out different input cases faster. And so you can see 72 test cases per second is actually considered pretty slow. And the reason it's considered slow for something like AFL is it doesn't have any insight like symbolic execution would as to the format of the input. It's not blind guessing, it's taking the input corpus, but it's guessing what those inputs are. So when you start to fuzz in real life, what you would want to do is make sure your computer is properly resourced to be getting hundreds of executions per second. And people will also take care on how they write the harnesses to increase the execs per second. Now we've been running it long enough here that it's found a couple crashes, and hopefully you did too. And those would be found in the output folder underneath the crash. Now, a crash for this particular program is just going to be a text file. And so you can see one of the ones that it created was called bad with no new line, bad with just one D as opposed to two Ds, and so on. So AFL will continue to run. Now, if you're actually doing this as part of, let's say, a CTF challenge, or you're trying to find a vulnerability, once you have a crash, you're going to want to investigate it. And so one way to do that is to install, of course, GDB. And I did not remember to install GDB inside inside this before sending it to you, but it's very easy to do. You can just use your common Unix utilities and install GDB, and then inspect those traces because they're just inputs. And please, people, interrupt me if you have any questions. So you can do GDB test me, and then of course you can just pick, here, let's pick out a corpus file. So let's just look at this one. And then you can just run it in GDB. And this is what I was talking about, which is one of the reasons, sorry, Clear, I was thinking it was a Unix Clear, why people love fuzzing. You actually have a test case and you have a backtrace. And so you can debug what's happening with the program. This is really important if you're a developer because the time to remediate a defect, if you actually have a working test case, tends to be much lower than if you don't have a test case. Now, I tried to go and see, has anyone actually researched this time difference? And as far as I can tell, no one has. I think we all just have to rely on intuition here, where someone kind of pointed at a bug in your code and said, hey, this looks wrong to me. It may take you longer to figure out whether it's really a bug and how to fix it. And then if someone had a test case where you can debug that problem. And so that's really all exercise one had was, can you compile with AFL and can you run it? I'm going to take a moment here to pause and see what experiences or what questions people had doing this themselves.
I have a question.
Mm-hmm.
So you give it the test case in the corpus. So does it like read the binary that was compiled with the AFL G++ compiler to determine how it modifies that to give it more input? Or how does that work?
Yeah, so what AFL is doing, that's a very good question. What is AFL doing? So when you type AFL fuzz, if we go back to here, what AFL fuzz is doing is it's just rapidly executing the binary. And on every execution, it's taking a file from that input corpus and it's modifying it and feeding it to the program. Now the instrumentation records coverage. It's recording what lines of code were executed. And of course, if there's a crash, it's reporting as a crash, but what does it do with that coverage information? So after the program terminates, it picks another input, modifies it, runs that program, in this case, test me, with that new input and says, if I got the same coverage, meaning I didn't execute any different lines of code, I'm going to throw out that second input because it's redundant. And so what is AFL doing for modification might have been part of the problem, part of the question. That's a good question too. And AFL actually documents it. If we go here to the docs, underneath its technical details section. So first, when I talk about it having coverage, this describes what AFL is doing for coverage. Its compile time instrumentation is looking at every branch of the code. So if you have an if then else, and it's instrumenting the shared memory map where it takes the current location and the previous location. So imagine this is the if branch and then where it goes to, or the else branch and where it goes to, and it's keeping a hash map of what locations have been hit. So here it's taking the XOR of current location, previous location, so it's taking the pair. If another input has hits that same part of the hash map, it knows it's getting no increase in coverage on that line number. When it goes down to evolving the input queue, this is covered underneath here on what it does. And so at a high level, if you run AFL long enough, what it's really doing is just taking that input corpus, here it was good, and it's flipping bits. Now, before it gets to just bit flipping, because you can kind of think of this as random, it has a number of different heuristics that it tries. So for example, one of the heuristics that it tries before just random bit flipping is it'll go through the input and it'll put 0, 1, 2, 3, 4, and those sorts of numbers. Because just empirical results show that if you have a program you've never seen before, you might want to try edge conditions first to automatically find inputs that crash. That was kind of a long-winded explanation, Devin, but was that getting at your question? Or is it still confusing?
Yeah, That did answer kind of how that exactly, like how it decides to modify it, basically given the input that you give it, and also how to determine what kind of coverage you're getting. So thank you.
Yeah. Yeah. And this is a very interesting document. I encourage people to read it because Al Kamtoff, Michael Zawisky, spent a lot of time coming up with how to efficiently calculate coverage. And I kind of lied a little bit. I said that he was just keeping track of coverage. He was just keeping track of the source destination pairs. Actually, he's also keeping track of things like how many times you execute a loop. So there's actually a counter here you'll see. It's counting it. And he uses that as a heuristic. It's kind of interesting because when you look at academic papers about things like coverage and minimal set, we would actually algorithmically use a different algorithm than he actually has implemented. But he's implemented something that he feels works either better or he didn't, in the particular case of coverage, didn't implement the academic algorithm for one reason or another. In our own research, what we found is his approach where he's keeping track of loop counts is actually good. You don't just want pure textual coverage. On the other hand, he's keeping what's called a min set. So he wants to keep track of the minimal set of inputs that exercise all current behaviors, all current locations. So when he went to implement min set, he didn't actually look up the min set algorithm. And if you have an algorithms course with the typical Revest handbook, you can find the algorithm in there. He implemented a linear greedy algorithm when the correct algorithm is a quadratic algorithm. And what we found in practice is AFL does a pretty bad job of keeping that minimal test corpus as you run it longer and longer, and they probably should be using the quadratic algorithm. So there's lots of interesting details and things to experiment. I can tell you in CGC, this is something, the CyberRun Challenge, where we didn't just use AFL or libfuzzer because they both kind of got the algorithm wrong. We put in the proper one and we got improved performance. And this is just minimal set cover algorithm. We'll pause there. What other interesting things do people observe here? Have questions about?
You mentioned, oh, sorry.
Oh, go ahead. I can ask second since you were first.
Okay, I was gonna ask, so you mentioned that it tries out like known, I guess like the numbers like 0 and 1 in order to because typically that's like an edge condition. So since there's it's not really like analyzing any of the lines of code that are in there. It's just choosing 0 and 1 because commonly those happen to be boundary conditions.
Absolutely.
It doesn't actually know anything. Okay.
It doesn't actually know anything. And so that's one of the things that you're trying to do when you look at research and why, for example, here it goes, fuzzing strategies, section 6. One of the things that we try to do when we do research is we're looking at symbolic execution. So symbolic execution would actually reason about the program as it's executed and come up with a new input. It's using an SMT solver to do that. So it's, we're using NP-hard technique, things that are trying to solve NP-hard techniques. So when you fuzz with a symbolic executor, it's orders of magnitude slow. You may only get 1 or 2 execs per second. But because it's not just blind guessing, we hope that it's much more intelligent about what inputs to get. What the latest research has shown, and you can read this with Jan and Fish's paper Driller. I don't remember if you were on that, Tiffany. I think it was before.
I was not on that. Yeah, it was
I think that
before
was a CGC
me.
paper. That was before you. Where they actually pair blind guessing with symbolic execution. And what that research kind of shows is that blind guessing is actually kind of good initially as a strategy. So it's good to try blind guessing, let's say, for the first hour, and then switch over to symbolic execution. So there's just a question of resource management. If you read through the fuzzing strategies, though, yes, they're just hard-coded. And actually, AFL is so well written, it's really easy to add a new strategy.
Right, and I would like to chime in and follow like that. So there are many more fuzzing papers that are recently published all about strategies or new strategies that are adding on to AFL. Yes, AFL++ is another one. And also like driller style is a fuzzing and symbolic execution combination, which is something that we call the hybrid fuzzing right now. But there are a lot of papers about that, and if you just search it, there's even a Git repository recording all those papers, and you can take a look at that. It's a lot, and it's very fantastic to look at them.
It is. I will just add one more thing that's important to realize. So fuzzers like AFL and libfuzzer do absolutely terrible on text-based protocols because if you look at their strategy, these are really looking for binary input. And so if you try to run AFL against, say, a web server with HTTP, often you're going to find worse performance because these were really optimized trying to find bugs in things like MP3 players. And so how do you handle text-based protocols is actually still somewhat of an open question. There's never been a tool quite as good as AFL for that problem domain.
So I've read the Driller paper before, and one thing I'm not fully sure of is how, like, in symbolic execution you have like path explosion. Like how does, and then it like increases exponentially, but like I didn't really understand how path explosion works.
Yes. So at a high level, every time you have an if then else, you fork. So you have one path for the if and one for the else. And so if you think of a program that's just if, you're doubling the number of paths each time. So this is path explosion, where every time you're analyzing something and you see an if, you have to double the number of executors potentially. And this isn't a problem just with symbolic execution. It's a problem with model checking. So if you go and read about model checking by Ed Clark, got the Turing Award, path explosion and taming path explosion is a big problem. And there's a couple things people do there. So first, they often use heuristics. So if you have a program, let's just say if B1, if B2, ooh, my VI skills are terrible, by the way, if B3. So if you look at this, there's 8 paths, right? Because there's 3 branches. Does that make sense?
Yes.
Yeah. So there's 8 paths here. So what people will do is, you know, they'll use heuristics. They'll say, hey, when I look at this this particular path, I'm always going to try to exercise the if branch. Or when you come up with something like, if we have a better example, like string copy buff input, which we all know is a bad problem. This is actually a loop, right? This is kind of like, you know, for while buff at I not equal to null, I plus plus, right? That's kind of what this loop is for string copy. What they'll do is they'll do things like, instead of branching, you know, on the first iteration, second iteration, third iteration, they'll try to do maximum number of iterations to try to find an exploitable vulnerability. So they'll employ heuristics. The second thing that there's a paper called veritesting, and this is used both in inside Mayhem as well as inside Anger. What this does is at merge points, so we call this a merge point right here. So this is a merge point, right? We have 2 different paths that merge at the same point. What it does is if we call the one for the if branch formula 1, the one for the else branch formula 2, it'll create one formula, which is F1 and F2. And so you end up with a formula that's linear in the number of if branches that you have, though in some ways this is a little bit disingenuous. I've represented the program in something linear in the size of the program. The SMT still has to do exponential work. So this is what this paper is about, and it's also an Anger, which is how do you create these formulas? And it's one way to mitigate path explosion, but you never avoid it.
Okay. Thank you.
Yeah, path explosion is a big deal. And I have a funny story on this paper, actually. I don't mind sharing with you guys. So you guys all know Fish, right? What is Fish known at ASU, Tiffany? Is he known as Fish or something else?
He is known as Fish.
I think,
Okay.
yeah, many people know about Fish, and Young perhaps as well.
Cool. So Dr. Fish. So Dr. Fish and I were having a conversation. So we wrote this paper and he implemented it inside Anger. And he was getting worse performance than without it. So we were trying to mitigate path explosion. It was doing worse. It actually turns out that there's this one paragraph here that says that we use hash consing. I think it's right there. Yeah, so we hash cons. This one section, these 3 paragraphs. So he actually just implemented the algorithm and didn't implement this. This is actually kind of, if you think about it, Hashconzing is a technique for managing it. It's a data structure management algorithm, but it's really kind of an implementation detail. It's not an algorithm detail. So he didn't implement hashconzing and he was getting worse performance. And it turns out if you try to do things like Vera testing, like this merging that I talked about, and you don't implement hashconzing, you get worse performance. And then when you implement it, you get better performance. And so there's actually quite a bit of systems research beyond just formal methods here on how do you actually make these algorithms performant. And then once he added this inside Anger, things worked out.
That's very interesting. I didn't know about that.
Yes. Yes. It was worse until he implemented this. Any other questions? I mean, I love the questions about path explosion. That's a really deep question.
I have a research question, but I can ask it later because I know you do have to cover some more stuff in the course.
Okay,
Or if we have time, whatever works best for you.
that sounds good. And as always, feel free to reach out at me. I'm dbrumley@forallsecure.com. Please do not email me at my university address. I have declared email bankruptcy on that account, and I simply don't answer it anymore. I know that that's not potentially ethical and people can judge me, but I'm just telling you the truth. I've declared bankruptcy. All right, so the second thing that I wanted to cover with you was actually harnessing an application. And so please go to the tinyxml2 directory. Oops. And if you look at the tinyxml2, there's a README here, which is simply a README for tinyxml2. I've provided a version of it, and this version has a bug. And so I wanted to talk about fuzzing, and in particular, show you how to find this bug in tinyxml2. And so if we go back to our README here, what we're going to do is we're going to write something I call a harness. So this is a really important term to know. So what is a harness? A harness is a little snippet of software that's used to target a specific function. This often comes up in testing when you're writing tests for your code. You'll write a little piece of code that calls the function you're interested in and maybe asserts that you get the correct result. And fuzzing will write harnesses to target important pieces of software that we care about. Or for example, if we want to test a library, we'll write a little piece of code to call the library, the part of the library that we want to test. Harnessing is also used if you have an application that's not amenable to fuzzing right out of the box to make it amenable. So for example, AFL and libfuzzer do not handle network binaries. If you have a network binary, a binary that reads from a file descriptor, a network socket, it just won't work. They only handle user input from normal files or from standard in. You can write a harness to replace that network functionality with just reading from a regular file. So this is something typically a developer would do. If you're a penetration tester, like you were going to fuzz something to go find 0 days, it would be something that you would be doing as a security researcher. So in this assignment, what I want you to do is look at, I love this example because it's so small, tinyxml2.cpp. So you have this intuition that AFL is going to be reading from a file, or producing a file, and then you run the program on the file. So the goal is to write a harness for tinyxml2 that loads the file that AFL produces and prints the result. And you need this print just because to find the particular bug, it'll speed up finding the bug. I've provided a file, a prototype of it right here, just for those of you who don't program as much in C or C++, I wasn't sure the skill level, so that you can get started. And then similar to the last assignment, you'll have to figure out how to compile this harness with AFL. And so when I've done this before, typically it takes around 25-30 minutes for people to do it. Is that an okay amount of time, Tiffany? Or do you want to shorten it somewhat?
We probably need to shorten it because the class will be finished in half an hour.
Okay. Well, why don't we spend a good 10 minutes just covering it? Because I think it's really important for people to try it themselves. Otherwise, all this is just, theory and no practice. So I'm going to give 10 minutes to our timer here for you guys to try to fill out this harness. And then I'll walk through how to solve it. All right, everybody. I don't know, was anyone able to write a full harness and fuzz it and find a vulnerability? Find a bug, I should say. Did someone say yes? I didn't hear that.
Could you repeat the question?
Oh, was anyone able to actually fully write a harness and fuzz? If the answer is no, that's totally okay. I think one of the things people run into in this exercise is the same problem that you have when you're a vulnerability researcher as opposed to a developer. When you're a vulnerability researcher, people will give you a code base that you know nothing about, and then you have to make sense of it. And a lot of your time is just simply trying to make sense of that code base, as opposed to actually writing, code for things like fuzzers. And so what we're seeing in industry is a lot of the responsibility people want trying to shift for writing those harnesses, they're trying to put on developers because they're actually intimately familiar with this. If you look at Google's fuzzing efforts, for example, they reward the developer for writing the harness. Google themselves don't. So let me go over how I would write the harness. And I have my little cheat sheet here because, of course, I did this ahead of time. So the first thing that I want to do is, well, actually, we don't need to do it this way. The first thing that we would want to do is we'd want to go into the tiny XML, and we'd want to, of course, open up this file. And we want to figure out, well, what do we need to do to write this sort of harness? And so typically what I would do is I would look at the header file for tiny XML2. And what you typically want to look for when you're first starting out is ways for that program, especially if it's like a library, to just read from a file, because after all, AFL is going to be producing a file to read in from. And so I start going through the headers and I look for constructors that take things like a file argument. Now, here are two good candidates. One is parse. This is just taking in a constant character string, and it says parse it from a character string, as well as load file. And you could imagine, I haven't looked at the implementation, but my guess is load file is just reading in from the file and then calling parse. And so this is the first function that I would look at and I would write a harness for. So if I go over back to my harness, what I would do is I'd create an instance of the class. And then it was called, what was it called? Load file with argv of 1. And then I told you that I would also call print. I think it says right here, print the XML object, and you can just look here to find the print method, but it's literally just print. And if you wish, you can also do things like going and checking if there was an error during loading. And so here, let me.
David, would you mind to zoom in a little bit?
Yeah, sure.
Thank you.
Control-C, Control+ is on fine. I just started using Spacemax, and I don't know how to zoom in. Are you having a problem reading this screen right here? It should just Control-C, Control+. Why is that not working?
Does it work if you do like Command plus?
Yeah, that's what I was doing. It doesn't.
Okay. Yeah, never mind.
It should just be that. I can come over here as well, and this is easier to do it. So I'll just have this over here as my little cheat sheet. And then close it out here. So one of the nice things is since we've mounted everything inside, did we mount everything inside? We should be able to just write it here and do and doc.parse. Oops, sorry, that's not the first one. We want to look at the first solution where we just simply load the file. And as I mentioned, you can actually, for example, check errors if you'd like. And how do you know which functions to call? You just actually just have to go through the documentation in the header file. So this might be an example harness that you write. It's very simple. It's just loading from file, it's printing, and then it's looking for the error, if there is an error. Then when you want to make this.
Oh, sorry. I just wanted to ask. So when you return the error, does AFL actually like also take that into consideration?
It does not. So
Okay.
this particular line, for example, really doesn't do much. And it would be completely safe in this case to leave it off. The reason that you might want to include it is, for example, if it took, for example, what I suspect is happening in print is that you have an invalid write, and then you need the invalid read to actually trigger the error. So sometimes by looking at the error messages or the error itself, although AFL doesn't use it, you can trigger the error. As I mentioned in lecture, AFL actually is simply looking for a Unix signal. It's not detecting a bug in the program. It's saying every time it sees a signal, a bug was triggered. That's its security policy, if you will. And then similarly, we have our makefile here. We can do CX. Ooh, are we running out of time? I thought this went till 1:30.
No, we still have 15 minutes to go. It's just like I was
Okay.
cut off. I was disconnected and I'm just back.
Okay. So we have the harness. Now, the second thing that you would do if you were going to be actually fuzzing this is you'd go and you look for a number of example XML files as your initial seed file. And we've included those under resources. Just due to time, I'm going to use the ones that I know that work for the solution. And so I happen to know if I look under resources, UTF-8 test.xml, and put that in, that this is sufficient to fuzz. So to recap, what I've done is I've simply just called the library and said parse the file as XML and then print it out. The way you'd fuzz would be the same thing, the same way you would normally fuzz. And since we've made it so that we're taking argv of 1 as the file name, you just call the harness with that. And it's saying that it's a slow execution. One of the things, if you start seeing things like this, you can, for example, look deeper in the code to try to find out better places to call, such that you get a faster exec count. But this should be fine for us. It should take about a minute.
While we're waiting, I don't know if this is a good opportunity to ask a question.
Yes, it is.
Earlier, you said that AFL isn't like necessarily that great for like, I guess, text-based protocols. So I was wondering if you would consider this XML file to be a text-based protocol because it's like text, or if it would be like a binary file format.
It is a text-based protocol, and AFL does work. It's just going to be slow. So things like bit flipping strategies typically aren't effective on text-based protocols. One of the things AFL does do, though, is when it's generating an input file, it will try to take 2 of the ones that it generated and splice them together in different places. Things like that tend to work. They're not the greatest solution, and you're not going to get the best result, but they end up allowing you to find the bug.
And since you mentioned, I guess, that certain strategies are like less like bit flipping may not be super effective on like text-based files, I imagine there's probably a way in AFL to like disable a certain category of like input generation.
So I don't think that there's a way from the command line. You would recompile AFL by just commenting it out in the source code. One of the things that you can do with AFL is you can provide a dictionary file of, for example, keywords, and then it will try, as I said, to splice it together. At the end of the day, these are all just ways to make it kind of work with text file. When you go and you look at people who are, for example, fuzzing API servers, they're typically doing it different. They're doing it by laying out an API specification with the data type, and then you fuzz with that data type. Does that make sense?
Yeah, that makes sense.
It's also an open area of research. I can tell you, as I said, there's really no tool like AFL that if you just give it a random text processing would succeed. And this is often like when you look at Python, although there's an AFL Python, why typically AFL Python isn't effective, because Python is really a text processing language, does really well with text processing. It's used for things like Flash for web servers or Django. You typically don't find as many bugs. So just like before, we found a bug, and you can look inside the out folder, and it produced examples of them. And you can just simply do things like take your harness and give it one of these. And you can see where these sorts of bugs occur. So this particular bug is in GetStream. Now, where would you go from here? So this is a very simple example of how you could find a bug using AFL and the process you'd go through. You'd write a harness to call the vulnerable code. Now, when we talked about coverage, when we wrote this particular harness, we're calling the default constructor for XML. That means that any sort of code that relies on a non-default constructor will never be called while fuzzing, no matter how much you run it. And so you can do things, for example, as an extension to go in and say, well, I'm going to write a second harness. And in this harness, what I'm going to do is when I create the document, I'm going to call the constructor, but use a non-default argument, for example. And this will trigger a different code path because now, as it's processing files, it uses, for example, collapsed whitespace, the collapsed whitespace algorithm. So when you write a harness, it's not just saying I'm going to read the file. Often what you want to do is try to vary. You're going to end up writing several harnesses that vary different things. I'll just put one more thing before we go to questions, because I want to leave some time for questions at the end. There's ways to get code coverage out of this where you take the input corpus that was generated and then you measure code coverage. And typically what this involves is just recompiling the code with like the LLVM or gcov options in your compiler, running the corpus through, and then you can browse coverage in your source code browser. What often people will do when they're doing vulnerability research is they'll take a standard corpus, like the test corpus from that program, or one that they use for fuzzing. They'll then gather that coverage information and see what's not being covered, and then go write a new harness for the thing not being covered. So it's very much an incremental process of saying, what have I fuzzed already? What hasn't been fuzzed or hasn't been tested? And going and trying to look at that stuff that has not been tested. So I noticed there's a couple questions in the chat. And so let me go over them real quick. So Kamel, would you like to ask your question? You sent me a question about machine learning.
So I was just wondering if there are applications involving machine learning with fuzzing or dynamic analysis in general.
That's a good question. So when DARPA ran the Cyber Challenge, they call it AI or artificial intelligence. And often we will call it AI as well, because that's the best way for people to understand it. And the reason people call it that is when you're fuzzing, you're generating an input, running the application, and learning from that, for example, through coverage information, the next one. However, none of these are using machine learning algorithms. So it's more of AI in kind of a very shallow sense. So there is some work on machine learning from Microsoft, for example, in distilling your corpus. However, the jury's still out. My personal opinion is machine learning is not going to be a huge benefit here. And the reason for that is machine learning, typically you have some sort of hill climbing or gradient descent algorithm. So it's smooth. You get closer and closer and you have feedback to know that you're getting closer and closer to some objective. It's not clear in computer security that there is a smooth, there's a smooth surface to getting to finding a vulnerability. And so I think that's why I'm a little bit skeptical. And when you look at like formal methods, program analysis, static analysis, why you haven't seen machine learning really being used there is because it's unclear what their objective function would be.
Okay. And I was also wondering, does fuzzing detect like race condition vulnerabilities?
Fuzzing can detect race condition vulnerabilities. You have to set up a security oracle to do that. So AFL, it was really intended just to be brain dead simple to use. And so it really only detects aborts. When people want to detect things like race conditions, they end up having to write their own security policy and have that inlined in the program. So really, there's no limit to what you can find with fuzzing, as long as it's what's called a property that you can find with an execution monitor. So there's this paper. This is not the paper. Execution monitor security. Well, I'll send it in Slack. There's a paper on yeah, here it is, enforcing security through execution monitors. Here's a set of slides about it, about what are the things that you can enforce. And so things like race conditions you can detect, but probably, I guess, in a weird sort of way. So an execution monitor, you're looking at each step of the execution, and you're deciding at each step whether or not the input has gone wrong or not. And so you'd have to frame your execution monitor in terms of that sort of policy. I'm sorry, your race condition in terms of that. So if I'm trying to think about this a little bit deeply, race condition. It would only be a subset of races, because typically race conditions are about sets of executions, not about a single execution. Right?
Right.
People do find other, like, for example, non-C memory safe vulnerabilities. So people have used it to find direct reach reversal bugs, for example, is one. And what they'll often do is they'll write their own fuzzer, or what they'll do is they'll write a little, you guys have done LD preload in hacking, right?
We have that.
Yeah, they'll write their own little LD preload with their security policy, and they'll fuzz it with AFL. And then anytime their security monitor, their LD preload security monitor has a problem, they'll just raise SIG abort, and AFL notices that.
I guess like AFL is more of a consequence capturing mechanism, in the sense that it can capture signals, it can capture signals such as segmentation fault or SIG abort. And then like race conditions kind of a cause of something, maybe a signal is triggered. So if risk condition really like triggers a segmentation fault, like something in kernel that caused that, cause a segmentation fault because of risk condition, then yes, AFL can capture. So, but then it really depends on what is the consequence that is caused because of caused by risk condition.
Yeah, and whether it's like you need multiple executions to demonstrate it, I think.
Right.
So there was also a question about how do you go about fuzzing an operating system? So there's something called KAFL, for example, the KAFL project. And what KAFL does, well, KAFL. So what KAFL does is it's the same thing as AFL, except for instead of what AFL is doing is it's doing a fork and exec, right? So it's launching the file with a fork, it's execing it on an input. And then when the program terminates, it's repeating the process. What KAFL does is it does this, but with a hypervisor. So it's starting up a program, it's taking a snapshot of starting up a hypervisor, taking a snapshot, giving the program an input, seeing if it crashes, and then restating the hypervisor state. And that's how people go about fuzzing an operating system. Benjamin, does that make sense? Yep. So Trevor asked, what are some advanced examples of oracles? So I have to tell you, actually, when you go and look at fuzzing, most examples out there that people are looking for tend to be things like simple memory corruption. They're looking for those sorts of exploitable bugs. Some other oracles you see out there are very simple, such as when you're fuzzing an API server, you're looking at the response code of that web server. You don't see a lot of really deep oracles. For example, you don't see taint analysis often being paired with fuzzing. And the reason for that is often fuzzing benefits from quick execution time. And as soon as you add a more advanced oracle that, for example, monitors each step of execution directly, you end up slowing down fuzzing. So that quick exec cycle really becomes less useful. The one exception would be really symbolic execution, where people will add in, pretty much arbitrary security policy. So at every step of the execution, they'll build into the formula, was some condition violated, and then do an SMT. But that symbolic execution is really the only place. I don't know of any industry-wide fuzzers that have an advanced Oracle. Tiffany, do you have a comment on here? This might be some of your research as well.
Yeah, but I just want to echo what you said. You're right. Like so far, only symbolic execution is used as an actual Oracle as assistance with fuzzing. And also this is based on the fact that usually when you fuzz, you will, like when you fuzz for a long while, there will be a bottleneck over there. So that like when you, even though you create more inputs, you still like keep it executing with fuzzing, you will not be able to get more code coverage. It's just a matrix for us to evaluate the completeness or the effectiveness of fuzzing. And that's why symbolic execution comes into play. Symbolic execution, or more specifically, concolic execution, they try to generate more inputs that will be able to cover more fuzzing. And then yes, it is more expensive, but it's going to help fuzzing in a way that is going to expand inputs to be more diverse in the sense of coverage in terms of the vulnerable program. So that's why, although it is expensive, it's well worth to be brought into the entire process. But other than that, I don't think that terms such as taint analysis or other detection execution monitors schemes, they're really helpful, because also that you have to run it every time that you generate inputs is going to be very costly, and it's costly in terms of every execution, which is way too expensive. And that's why I think it's just like it's not economic to do that.
Yeah. This is the paper I was looking for, enforceable security policies. So these are, talking about security policies that you can enforce by dynamic analysis. It's a good paper to read. It's one that actually requires quite a bit of critical thought as well, because you'll see things like he says information flow isn't enforceable by an execution monitor, and yet you'll find people who are enforcing information flow via execution monitors. And really what he's talking about here is the most general sense, but you can find subsets of that are actually interesting in real life to enforce. So this is kind of standard reading for anyone starting research on it, but it's one that it's good to have in the back of your mind, but you have to kind of think carefully about it and then come and revisit and look at his definitions, because the definitions are sometimes too general to be useful. Well, I want to thank everyone for having me here today. I know, Tiffany, you're saying that the class ended at 1:15?
Right. Yes.
I wish I could spend more time with you. Hopefully you got excited about fuzzing. It is something that I'm seeing, if you want to go the industry route, or you're looking at like competing in pwn to own, it's something that I see pwn to own winners like Fluorescence using, GeoHot using, people like that, along with, of course, considerable manual analysis. But it's also an amazing research topic.
Cool. Thank you, David, for being here. And guys, let's just join me and thank David again. I'll just clap my hand, and feel free to clap on your side, mute or unmute, whatever. But yeah, thank you. And I will, if you don't mind, I'm gonna post this video to YouTube, or I can also just share that internally. It's gonna up to you. I can reach out to you and talk about that later.
Sure, I'm fine with YouTube.
Thank you. Yep. So yeah, guys, that's pretty much for today. And as David mentioned, if you have any questions to him, feel free to shoot an email, and he will answer you with those questions. Okay, that's it. Thanks, guys. Let me just stop recording.